acting on a ring or disk using vector addition. To practice adding force vectors graphically and mathematically in a simple geometry where two of the vectors are perpendicular. No, this is for actual lab. This lab sheet is our actual lab. But the virtual one, you just have to make sense between it and the virtual one. So it is not the same thing. So it's not that this one is written for the virtual labs. No, it's not. It's written for using the force table in general. So you'll pick out your cues from this information to actually able to do the lab. So remember what I'm saying now. So a person get the sheet and say, oh, sir, so we can have a discussion on it. This is to actually inform you about the force table and the principle behind it. So in this experiment, the Pascal force table, which is not necessarily one that we are using, is used to apply 3 forces to a central ring or this, so that the central object is in so-called static equilibrium. So right inside here is where static equilibrium exists. That is the object has 0 acceleration. So it's not moving. The net force on the object is therefore also 0. All right? That is for the ring. These forces are exerted by the Earth's acting on masses suspended from string that run over pulleys. Each string is attached to the ring at the center of the table. When the ring is centered over the middle of the force table, the direction of the applied force can easily be determined using the angle marked on the table itself. In our case, we can see where it is. And it starts at 0 down where we have F3 force. To check that equilibrium has actually been attained, pull the ring slightly to one side. Then release the ring and check to see that the ring returns to the center. No, we don't have to do that because we can see when it lines up with 0. If not, adjust the size of the hanging mass until the ring also returns to the center after being moved in direction. You don't have to follow all of this. Our simulated one will tell you. You can look at it and you know when it's lined up with that 0 line there. Right? So this is just a guide. And this is also giving you a guide as to how to draw a force vector, representing force graphically. And this is only tell you how when you walk. So we know that if we walk apart due east 1 mile and then walk due north 1 kilo, we end up at 1.15 because you know you're using the tan there from our starting point. As the crow flies, right? So we are now northeast of our starting point, angle of 40 northeast. If force can be represented by a vector, they must have these same property. A force of 1 Newton to the east add to force of 1 Newton to the north should add together to give a net force of 1.1 Newton directed to the northeast of an angle of 45. We want to demonstrate this property of force. So that is us giving a mumble jumble. I have put in some measurements down here. So what I've done here, I said position 1 pulley to apply a force of 248. So you can put that in and you scroll up to 248 for F1. Call the force exerted by the string that runs through this pulley F1, which I call it F1 already. Position 2. The other one now, second angle, you call that 98. So I've done some adjustment. This is actually from the simulated one. Call the force exerted by the string run through the second pulley. The position the third pulley to apply at an angle of your choice between 0 and 80. So I put 0 and 80. I will keep it at 0, right? And then I balance these two. And then you see. So your angle total mass of 103, ignore this part, on the string going over this pulley. So you ignore this, you put a weight. The weight that we're using, this weight should have been changed. It's up to what? 90. 0 to 90, I'll call that, or 10 to 90. I think that's the range that we have. So and of course, I'm trying to remember if they have any additional weight. Remember that the mass of the hanger in the regular experiment you would have had a mass of the hanger. In our case, I'll need to look back at it to see if it gives you anything for the hanger itself, or it just automatically. So we need to check for that. If there's a 10 kilo for the hanger, I'll have to look back and open the slide from starting when it brings up that information to just double check if there's anything for it. Meaning what I'm talking about. Let me just remind you. So these are the hangers down below where you put the weight on. I'm just trying to remember whether or not it didn't give me any information. And I'm saying all of the information is coming up here. I don't know why. As I tell you, these simulated things, you have to get used to them. But it's not giving me anything here. That's for the weight 2. And this is, so those are weight 2. So you have the angle that you move and you put the different weight on it. It says suspended weight M1. The mass of the holder is 10. All right, here it is. It is 10. So whatever weight you put on it, that means it will be 50. That's another consideration. And look at this one. All of them is 10. So all of them, the hanger is actually 10. Right. So whatever weight you put on this, you had 10 to it. So the hangers are 10. Yeah. Right. So that's what I'm clarifying right here. But we'll come back to it. What we're going to do now that most of the persons are here, we are going to go to our regular slide. Right. So we are going to go back to shear force, and then we later on down when your brain get tired, we go around and play with the lab. All right. So that's the strategy that I'm employing this afternoon. All right. So yesterday we went through a little bit of shear force. Now, who don't understand shear force so far? Anything that I need to recap? So I'll recap this afternoon. All right. So yes, we had this problem. Yes. We had this problem yesterday. It says draw shear force and bending moment diagram for the shaft. Where are the shaft? This is the shaft, and you have this bearings here, and a bearings is right here. All right. The support at A is a thrust bearing. So you have a bearing here, and the support at B is a journal bearing. So there are 2 bearings and it's running into it. All right. At this point here, B with his midspan, there's a 500 kilonewton being applied to this part here. So this is A, B, C. What we did yesterday, we draw a shear force for this, and we consider this a beam. All right. So we consider this a beam in our whole term. We call the shaft a beam. And therefore we're able to draw the shear force for it. So we cut between AB, section AA, and we cut here, so again, section BB. And based on that, but first we had to draw the free body diagram for this. And our free body diagram, if I was to remind you, let me pick up a writer and I hope you can see it. Well, you won't see it, I will use it as a pointer. So what we did was to draw the free body diagram. Wow, that is bad. Let's go again with that. So I'm just refreshing those persons who may have been late yesterday, so you get a chance to get a little refresher, so you can follow. Now let me see if I can draw a little bit better. Let's go at it again. So we have, wow, this one is worse. Wow. All right. I'm some point in time I'll do a little bit better. Yeah, wait a little further. All right, so we have the straight a beam supposed to be straight. We have midspan 5 kilonewton going down. You have your support here, and in this case it's just a bearing, so it just have 2 support. And this is A, this is B, and this is C. So this is AY, and this is CY. From that, we normally go and find these 2, but we can actually look and know them. If we have a 5,000 coming down, and you have two support and they're equally apart, then you know that this is automatically 2.5 kilonewtons, and this is 2.5 kilonewton, right? Because it's balanced. So now that we know that this is 2.5, so I didn't go through the process of finding it. We cut across here and we call that AA. Section AA, when we do for method of section in shear force, what we do is we draw it. And down to the point where we cut, we call that X, some arbitrary X. Now we know that there's a shear force on your cut and you shear the beam. So there's a shear force coming down. There's also a bending moment at that point, which is going into the positive direction, which is the anti-clockwise. So we have two forces. Now this is 2.5 kilonewton. So from that, using the sum of y, your equilibrium equation, because there's no x, you can say 2.5, which is positive minus v, because shear force is a force, you know. But we use v to represent shear force, and that equal to 0. So therefore, your shear force for that span is 2.5 kilonewton, right? So up to, so all of this span here, right, and we normally call it x, as we said. This is represented by x. Then we move from here and we try to find BC. So we have to go again and we draw again. When you draw, you put in everything man did before. So it's R, you know this is 2.5. Come on, writer. 2.5, don't mess up the thing. All right, and then you have, this is 5. Now, you know that this distance was what? 2. Eh? You know that. Now, the distance you cut down, you cut some arbitrary distance, which you don't know. Right? Right. So, but the distance between here, mathematically, you know it's going to be x minus 2. Some distance here. All right. We know that we have a shear force coming down and we have a bending moment. We soon get to the bending moment, but I'm also reviewing the shear force aspect. Now, here now, how many forces we have? We have 3. 1, 2, 3. So this is an additional one right where you cut this plan now. So we need to use the same sum of y equal to 0. And we're gonna find out what is the shear force acting between right here. So the shear force, and this is kilonewton. So the shear force is going to be 2.5, which is going up, the reaction. One that is coming down, which is minus, and one that is going down, which is minus v, equal to 0. So the difference between that is 2.5 equals to what? V. So therefore, your shear force for this span is minus 2.5. But over here, it is 0.5. Right? And from that, you are able to sketch your graph. And we normally put everything behind, but I'll show you on the next slide. So let's jump around. So here we have it. So for the first one, this is what we did, and it was ranging between 0 and 2. So that is it. And it was 2.5. And for the next one, see it here. Now, we also include what we call bending moment. And this is very important. So it's not just we draw a shear force, but we draw a bending moment. We go back and look at the actual result afterwards. Let's just take on what is the bending moment. The fact that you did the shear force and you use the equilibrium equation f of y, we can also do moment. Because we have a moment here, eh? So let's see. So the sum of the moment equal to 0. Let's look at the first one here. So the moment, we have a what? We have a moment here. So the moment, and it is positive, says m. Now, what is the moment between this part here? From remember, you're taking moment at this part here. So it's right here taking a moment. You know that you have this moment there already, always there. That is positive. So you're taking moment from this, you know that you're going to have 2.5 times x. So it's going to be minus 2.5 times x equal to 0. Transpose for m, and m is equal to 2.5x. So that is your bending moment. So whatever value of x that you keep putting in this formula, from 0 to 2, you will be getting what is the bending moment on the span of this going right up to where B is. Right up to where B is, you would have gotten it. So if you put in x equal to 0, right at A, bending moment is 0 at A. If you put in x equal to 1, you find that the bending moment is going to be what? 2.5 at some point. If you put in 2, the bending moment is going to be 5 up at where B is going to be 5. So we'll look at that later, but you put in the same range value in this formula, this expression here. So what you have actually come up with, you come up with one for shear force and you come up with one for bending moment. Let's take on when you cut the other part of this the frame. So you're cutting between A and B before, and then you cut between B and C. You remember that this was what you cut. So this will cut this section now. Let us come up with the expression and show you how they come up with that expression. We look at this one before and we'll see how they come up with this expression, that V, the shear force over this section here, is minus 2.5 K, as I explained previously. For the bending moment, the sum of the moment is equal to 0. All right? So that is a formula that you have, and that's what we're going to use now. We're going to take moment right here. The first moment we have is that guy that is positive. So see it here, M. So it's M plus, let's take moment now. We take moment before and we remember that it's going to be what now? From here, taking moment from this point, we have this force times 2.5, and it is what? Minus. So let's scratch that. I don't want to mix it up. So it is minus 2.5, because that is going in what? The clockwise direction times x. So it's 2.5x. All right. But this guy is coming down in this direction also now. Well, what is this distance from where you cut? It is x minus 2. So it's going to be plus 5, come on, times x minus 2 equal to 0. So this gives us, right? So there's a minus here. We're going to put that over that side. But let's work it out first. So m minus 2.5 x plus, where's the 5 here? There's something eat out the 5. All right. So expand that bracket, we get 5x minus 10 equal to 0. So that works out to be what now? It works out to be positive 2.5 here, minus 10. Not true. If you transpose that and left the m that side, you get minus 2.5. Isn't it so? You get minus 2.5 now. Come on. Right? Plus 10. Right? So that is what you have there. It's minus 2.5x, pardon me. I left off the x. So it's minus 2.5, 10. See down here? Only that they write up in a neat way down there. So in other words, what we have there is m is equals to minus 2.5 x plus 10. So you get an expression for your bending moment, right? And that expression for your bending moment, consider everything from A go right up to C. It just don't incorporate just B and C now. So anyway, you would put, but I tell you, so if you put, but let me tell you, even though it incorporate everything, it's really specific to the BC section. So if you put in, so you have to put in values from B up to C. The values from B up to C goes from 2 to 4. Can remember, you know, from the middle up to C was what? 2, and the other length was so it's 2 up to that point, so it's 4. So you put in values anywhere from 2 to 4 in this expression here. You put a value of 2, what would you get here? So you'd have gotten minus 5 plus 10. So you'd have gotten that it is the bending moment there is what? Sorry, it would be 5, positive 5. If you put 3, what would you get? You would get 3 times that, you'll get what now? Minus 7.5 x, sorry, 7.5, pardon. Is that what you would get? Am I correct there, guys? And then you would have plus 10, so you get positive 2.5. So when it is 3, it is positive 2.5, and that is the BM. That is not shear force anymore, it is BM value. When it is 4, what would you get? You would get 0. So M is equal to 0 at 4, because you know that 4 times this is minus 10 plus 10. So it's 0. So your bending moment must come back. And it start at 0 and must end at 0. Remember, this one start at 0. 0 in this formula is 0. When you put in 2, you get what? 5. So you get it up to where 5 is. So you get it gone up to 5. Bending moment was 5 at that point. So let's look at it now so you can understand it. So these are the values. So prior, we looked yesterday, so we saw our shear force going up here. So you climb up 2.5, positive. That's a reaction, and it comes right across the span of 2. At this point, you have the 5. So this is positive 2.5, but you have a negative 5. So positive 5 from positive 2.5 from negative 5 gonna give you what? Minus 2.5. So it comes down minus 2.5 right down here. So it's positive up there, positive 2.5, but it's minus 2.5 here. It's come right along this span here, so it goes right across. So it reach here. When it reach right here, this reaction is positive. This is minus and it's positive, so it give you back 0, so it close back here. So it come right here, so unclose. Sorry, let me just close our window, please. One second. All right. So, all right, my dogs are attracted by neighbors. All right, let's go. All right. So right here, you notice that the shear force is minus 2.5 right here. So as it comes right down to here. And that's what your shear force looks like. But what about the bending moment? Our expression that we had before, let us remind ourselves what our expression, we can actually write them. So one was 2.5x and the other one was minus 2.5 plus 10, right? All right. So we know our expression. So we had expression of minus 2.5x. That was it. Was it minus? No, it's positive. Positive. And the other one was this one was a minus 1 plus 10. All right, so it was 2. So for the first part, this was the formula. See here, it's actually there. They're there. So it's 2.5. So 2.5, when you put in anywhere, this is 0 and this is 2. So when you drop 0 in it, it drop here. When you put 2 in it, it carry to 5. So you notice for simple support beam point load, you get a triangle. I'm telling you some key things now. It's a triangle. For shear force for a single beam, it's a rectangle. You remember I said that yesterday? So when you drop here, you come straight up to this point. Now, all right, when you reach up here now, this equation kicks in. So from 2, when you drop 2 into this guy, what do we say? You get back the 5. So you know, so it's right here. So when you put in 4, what will you get? You get 0. If you put in 3, what did we say you get when you put in 3? 3 give us 2.5. So it dropped somewhere at 2.5. So this is 5, it dropped down to 2.5 midway. That's 3. All right, and this was 1. When this 1 is 2.5 also. You recognize that? Because remember, you know, over here is 5. Well, this is 2.5. So it's all positive. When this one is all positive, everything is above the positive. Yeah. So you have here, you can always have an axis down here. So there's nothing down at the negative part of the axis of the bending moment. If I was to ask what is your maximum bending moment, your maximum bending moment is 5. Right? Note that. Your maximum shear force is 2.5. See there, positive 2.5, and the maximum bending moment is that. These are key things. I will ask you these in exam. So you have to take note of what is maximum and minimum. So if I was to ask you minimum bending moment, and it is minus 2.5 because it's dotted below this point. For this one, it really don't have a minimum. You just call it 0 if you want to call it. You just say 0. That's the lowest bending moment you have, lowest value. All right. So that is what it really looks like. So now typically you draw your frame first. You draw your shear force. We normally don't use and call it SF. B, and this one we call BM. So, right? So this is your shear force. This is your BM diagram. All right, and that is really what we say. So it says, as look at the notes. It says start at 0, increase linearly to B, and therefore decrease to C. So you go linearly, then you can't. Then you go down, you decline. And these are for a simple beam, not for a compound beam. All right, so we need to look at another one. So let's just jump on. All right, this lovely one that we looked at yesterday. So we looked at it for the shear force, but we're going to look at it for the bending moment. Remember, the entire span is 9. It has 2-point loads. You have a reaction here. This is a pin, and that's a roller. So you normally have a force here, and you normally have 2 here. But for the X is not relevant in these problems. You can actually ignore them. All right, so let's move on. So we worked out, we use our moments, we use our equilibrium equations, pardon me, sum of y and the sum of, and the bending moment equation. We forget about x. As I tell you, x is not relevant, and you are able to find, you use it. Consider using bending moment. You say that take the bending moment at B in this case, and everything there is 0, and you take your bending moment, right? Angle having RAY in it, find RAY, then you use this equilibrium equation, which you know already. You just write this one and put the value there, and you get it. Remember, O-level physics, same thing. All right, run on. And we had cut this point here, and we're able to write the expression, which was basically that. 33.3 V for this section. And for that section, what was it again? Was it 13.2 or something like that? This section was, I think, 13.2, and this was minus 2 point something. So we do the bending, the shear force for each section by cutting each section simultaneously. So we cut that first, and you get this expression. So that was the first one expression. The bending moment was for this. Remember, your V would have come here. So you see, you have a bending moment. So for the bending moment, you know your distance here is x. So it's x times the force, but it is going the opposite direction. Right? So see it up here. So it's minus, but when you resolve it, it becomes positive. So it gets 33.3x. All right. So you take moment at this point. So it's x times that, which is minus, but this is plus. Remember that. Transpose, you get that formula. So that's how you get the bending moment for that. Who don't understand that? Do I need to go in more details? Have I left you there?
Yes, sir.
What is it that you don't understand?
Sir, my Wi-Fi is kind of shaky, sir. So I
Mm-hmm.
missed out a couple points. Could you elaborate on your point?
All I'm saying here, yesterday I showed a very same beam, and I looked at only the shear force, where I said that you cut between these points and you're able to write your shear force expression, which was this one. You cut here, see it here, and you put the V here, down to this point, your X there. So your X is there, some arbitrary distance X. You have your shear force, and you have this reaction. You resolve these two using your sum of y equal to 0, equilibrium equation, RAY minus V equals 0. Because this is representation of shear force, that V. Remember, it's a force. One going up, one coming down. Resolve it using this expression. So you get this expression as RAY equals to that. And you know this is equal to 33.3. Now that is a force, so it's kilonewtons. All right. So therefore, you get your shear force as that. The bending moment, likewise, using your sum of your moment across AA. So this one is written perfectly. Well, see there, section AA, where you cut, you take moment there. So M minus RAY, because this, you take the moment, says RAY times X minus M equal to 0. So therefore, M is equal to RAY X. And those are your expressions. So if you put in anywhere between, your range here is going to be what? 0, between 0 and 2. So you put in 0 there for this guy here. You see that your bending moment will start from 0. You put in 2, you see that it's going to go up to what? 66.6 or something like that. If you put in 1, it's going up to 33.3. All right, let us look at what happened here. So let's go to the next slide. When it comes to B, it start all over again. So for the shear force, review here, you cut here. So here we have it. So you have the force. 1, 2, 3. 3 forces. Shear force, point load, reaction. You use a sum of y formula. Sum of y equal to 0. So it's RAY minus 20, which is going down as minus shear force, which is equal to 0. Transpose everything. Don't you have RAY, which is 33 minus 20. So you get 13.3 kilonewtons. All right. Now this one is sum of this is a bending moment now. What do I have here? Wow, what is it? Is this correct? Why do I have him here? F. It's not F, is M alone supposed to be there? No, F not supposed to be here. There's an error right here. I think when I was writing it, it's really an M. It's really taking a moment at B. So this F is not supposed to be there. Hello?
Sir.
Mm-hmm.
Why is the moments error going that way, sir?
This one?
Yes.
All
I don't
right.
understand
Remember
that
when
part.
I started out? All right. It is always going to be going into the positive direction. So there's always going to be a bending moment where you cut the beam. And it's always going to be a positive bending moment. So you can take that. That's gospel. So wherever the beam is, wherever the beam shear, there's a bending moment, but we consider that bending moment to going into the anti-clockwise direction. Just like we have a shear force, have a bending moment at that point. Take it as gospel, like what written in the Bible. All right? So it's a given. Now, so there are two things that is happening wherever you cut the beam. You have a shear force, which is minus, and you have a bending moment that is positive. Two things. All right. So wherever you cut it at BB, which is right here, you're supposed to take your moment again. It's two things supposed to be happening here. So this is a bending moment. Did we do the, you know what I think missed out here? We do the shear force already, so that's all right. So we have that already. This is only M. It's M supposed to be, so actually supposed to be just MBB. But I have F. That's the erroneous. If you see it in the slide, please delete it. It is just bending moment alone. It's an error there. All right. So what happened now? Let's go with it. So we are going to take moment right here. Now you're taking moment here, but you have one already. Remember, like when you're doing equivalent force and you have a bending moment in the system. So you have one already and it is positive. Always positive. So M minus is the first bending moment you're going to take. Your first force, and you're taking moment here. This is going into the what now? Clockwise, which is minus. So it's RAY times X. It's time X, you know. That the distance down to this arbitrary distance is X. So it is minus RAYX. All right. The next one you have is between here and here. Do you know that distance? No. So the distance here is going to be what now? X minus 2. That distance. All right. Now that distance, so it's going to be, but it is going this way. This force is going to take it into the positive direction. So it's going to be 20 minus X minus 2 equal to 0. You work out all of that, which is a little bit of simple equation. This is 33, so you put it in. Minus 20 minus X. When you finish, simplify that, you get 13.3X plus 40. Positive 40. Now, that expression is going to be between, what are the values of that expression? That expression is going to run, for X, what are the values now? Where it runs? It's going to be running for X X is going to be 2, and I think what was the other value there? Let me remind myself. 3. So it is between 2 and sorry, it's not 2 and 3. It's 2 and 5. It's between 2 and 5, which you get 3. The difference between 2 you get 3. So the range there is between 2 and 5. So if you put 2 in here, you're going to get what? 26 point, what was it? 26.6. So 26.6. I think I rounded out 26.7. Right? And if you put 3 there, what would work out for 3? Let me get a calculator, because you know you guys don't like participating. Make my own calculator. All right. So if you put 3, it's going to be 13.3 times 3. So it's 39.3. Plus 40 would have been your bending moment. So you'd have put everything. So your bending moment at that point would have been 79.7. But we're gonna go around and look at our graph. So you don't just put in value of X, you'll have to add this. So the first one would have been 13.3 times 2 plus 40. So the first one would have been 66.6. Right, we had the 40 to it. So you understand what I'm saying? But we're gonna go around and look at it. So that would have been the range. Let's go now and look at doing the one down to here. So it's really forming some expressions. So the shear force for this one, you would have gone and you write your equilibrium equation for the Y for the shear force. Now, how many forces you have here? You have 1, 2, 3. 3 forces again. But plus this one will be 4. Because you'll have V right here. See it here? So let's count it. V, 40, the 20, and the 33. So you have 4. So let's go and write it. So it's RA minus 20 minus 40 minus V equals 0. So it's going to be RA minus 60. But you know RA, which is 33.3 minus 60. So it's give you a minus 26.7 for that shear force. So that's your shear force in between this span here. That span is going to be what? I think that span is going up to be, is going to be 5 and 9, between 5 and 9 would have been. So up to here would have been 5. And the maximum up to this point would have been 9. So it's between 5 and 9 would have been your range values there. The ranges. All right. Your bending moment now. So you have 1, you have a bending moment here. See it here? This was, we have BB here. This is an error. This is CC. Sorry guys, this is CC. And the problem is I don't know if I can edit them out. Sometimes the software give me a problem. Those are CC, because it's this. What did I have before around there? We have BB around there already. Yeah. So this is CC. All right. So these are CC. Now, at least you'll see it in the video. So these are CC. Now let's look at it. So they have 1 here, 1 bending moment here. Let's take moments now from this point here. Remember, this is where you cut it. So we're gonna take moment now. The first one we're gonna cut is this one, RAY, which is 33.3 times X, and this is minus. See it there. The next one is going to be this distance here. What was this distance here? This distance was 2, this was 3, and then this distance would have been what now? It would have been X minus 5. Everybody agree? Remember that this is 5, 2 and 3 is 5 here. So if I want to know distance, remember this is the greatest distance, which I don't know. So it's going to be the difference of these two distances minus X. So that is how I get that. So I go here and I say 20 times, this 20 is going in the clockwise. In the anti-clockwise, which is positive. So it's going to be all is going to be all of this distance here. Let me see now. Do I have it correct here? What do I have here? Let me see what I have here. I have x minus 2. X minus 2, x minus 2. Yeah, this distance is really x minus 2. It is really, in a sense, it is really x minus 2. We can remember before we had it as x minus 2. So really and truly, this is really x minus 2. Because whatever you had before have to follow. So in other words, what I'm saying here, let me just backtrack. To be consistent. Remember, you had it as x minus 2. So if you're taking a moment, you have to use that value. You can't get around it. You can't use 3. So it's x minus 2. All right. So it's going to be, so your total distance here, so is going to be, I'm looking to see, yeah, because look, let me tell you what's a practical thing of this. This is the distance you want. Let me show it to you. This is you have x coming down here, but this is the distance you want. This is 2, so this is automatically going to be x minus 2. Can you see it now? If I put it down here, can you see it?
Yes, sir. Yes, sir.
Right, so that distance is x minus 2. So don't put it up here. Up here, so might not help you to see it. It's actually distance from here down to the we're taking moment. So this is x minus 2, but it is coming this way, guys. All right, so that is positive moment, which is anti-clockwise. So it's 20 times that. The next one now, guys, is this distance. So from here to here, so it's 5. So this distance down here, so that I want, it must be x minus 5. Right? Right? Because this is all x. So this little distance that I need between here, so knowing that from here to here is 5. So right down to here is 5. So if all of that is 5, then what is this little distance here that I need now? So it's going to be 40 times this little distance here, x minus 5. All right? So it's going to be 40 x minus 5 equal to 0. All right? So it's a little bit of algebra jumping here, so we're just using symbols. So we're just using the symbol. We forget about these. They're relevant, but we have to forget about them. We put them down here. It might be a little bit more relevant here. You can see this. So this is all of this distance is here, some arbitrary distance x. But I know from here to down here is 5. So this must be x minus 5 for this little gap here. So it's 40 times x minus 5 equal to 0. You work out all of that beautifully. Transpose, you carry that positive side. So this come over positive. That will come over negative. And that will come over negative. And you break it down, you'll get minus 26.7x plus 240. All right. And that is your BM, bending moment. All right. And the bending moment is going to be Newton meter. Sorry, Newton meter. You know it's bending moment already. Force time distance. All right. So that's its unit. When up here is Newton or kilonewton, depending on what you're given, then this is Newton meter. All right.
So that bending moment is at CC.
Where to me about CC? I don't get you. CC meaning. Where? Here? That's what you're talking about?
Yeah, where's that bending moment? That one that just work out.
Oh, it is between here. The value is between here, right? That one is right between here. So this expression, what's the range for this expression now? This expression range would have been 5 to when x raised by 5 to 9. So it's between this little here, that distance. So whatever value you put between 5 and 9, it should give you the exact curve. So these expressions that you find, you see, guys, it's like you're drawing a graph, but you want to know, get your expression to draw your graph and see if right part. This method of section help you to get your graph. And see it, it's a section CC. So we know that this was an error down here. So now we're going to look at our graph. I'm hoping that I did draw the graph. I don't remember if I did. I need to go to presentation so I can keep track. All right. I'm not seeing a graph there. Hold on. Didn't I draw it? Yeah. All right. So this was a shear force that I did yesterday. I'm gonna look for the bending moment. It should be in the slide. I hope I did incorporate it. It should be there. I wanna look for it. Wasn't there? Oh, still looking. Should be there. I asked you guys to do this one yesterday. I suspect that you haven't worked on it. I'm looking for it. All right, so you see it? So in bending moment, you normally use two terms, sagging and hugging. So it's when the beam positive bend, this way, you said you consider positive bend, and this is known as negative bend. Where they call it hugging.
Sir. Basically, you just flip them up like one, you know, smiley face and frowny.
Yeah, something like that. That will help you if you remember them if you want to. All right. So it's a bending tendency of a beam to bend due to force acting on it. Huh? All right. Magnitude equals the sum of the moment of the force on either side of the section and can be determined at any section along the length of the beam. Right? So the bending moment is a reaction minus the moments of the load to the left of the section. So let's look at the graph now. So here we have the graph. So that was the shear force and the bending moment is here. So for our first expression we had for AA was just this. So between up to this point was 2. So when it is 2, it reaches up to the maximum of 66.6 Newton meter, right up here. So you normally have the beam here, you normally draw it in this order and it is good. You draw the beam first, then you draw the shear force and you do the beam below it. It helps you to keep track so you can see where your weights are. All right, so when the 20 acting at this point, you get a bending moment of that. Now, for the span between B at this distance here, now see the expression here. So I have them here, so you can check it. So from here, so it was 2, and this would have been 5. So when you put in 2 inside here, so you should get back the same value in the same expression. So if you put in 2 here,
Sir, I'm not see pointer we have showing.
Pointer. So when you put in 2 here, you get back 66, positive 66, because this drop out as 0. You see that? Everybody see that part drop out, so you get that value. But when you put in 5 now, what do you get? You get this value here, 105, because 5 times this, what 5 times 33 gives you what? 166.5. And when you put in 5 here, so you're gonna get 3 times 20 minus 20, which give you minus 60. So you take away minus 60 from that, you're gonna get end up with 105.5 right here. So see it here? And that end up to be your maximum bending moment in this thing. See that? So you have M at x equal to is that. At 5, you have this. This is your maximum bending moment. I need to point that out. I didn't have it right in the slide, but that's your maximum bending moment. See it up here? Maximum shear force. What does it? See there? 33.3. So you must, if I ask you for those value, you must be able to tell me. This can't be maximum kite down there. Minus. That is small too. So that must be the maximum. And your maximum BM is the highest point on your graph. So this is maximum BM. And you know, this should have been really kilonewton meter because that is kilo. So it's really kilonewton meter. All right, but the most important thing, you know, that unit is really Newton meter. All right. So at this point here, what about CC? CC start from here to here. You see, if you drop in 5 here, you're gonna get back the 105. See, from this expression here, you notice is a continuation of this expression plus this piece. If you drop in 5 in this, you're gonna get 105 here. This is algebra. You remember you're doing high school, you say, why teacher give me algebra? Our simple expression. This is the usefulness of simple expression. All right. And we had worked out this. I think this was a smaller expression I had in the slide before, but you know the value for this. So you can work out this. It was something like what? 266 minus some value. What was it again? Can we sneak back? It was some value there. See it here. Was it that? Yeah. So it's minus 26.7 plus 240. See? Yeah, that same expression there. Let's jump back over. Right. So that's what it works out to. So if you put in 9, you should get 0 here. When you drop it, if you put in 9 in it, you're gonna get 0 right here. And somebody can test it, please, and confirm. So the expression would have been minus 2 point. What was it again? So it should have been m equals to minus 26.7 plus 240, something like that. X. I think that was the expression. If you put in 5 in this expression, you should get the 106. So it will be minus.
Sir,
Yeah.
you see in 9 way that talk about for 0 forget and really 0 me get 0.3, negative 0.3.
Yeah, man. It's yeah. So maybe some round off. But if you put 5 in this expression, you will get 106.5. And if you put 9 in this, you will get it probably approximate. Remember, so we reduce it to round off and writing it. But really and truly, so it's minus 26.7 times 9 plus 240. A point 3, man. Lord, brother, it's so terrible. Minus point 3, it's so terrible, man. In Dixon, it's technically 0, man. You're too terrible, man. I look around half one, lesson. All right? So it's really 0 at this point here. So. All right? So, and that is what we call shear force and bending moment. So in the exam, when you see a question, you're going to lay it out just like this. Negative shear, positive shear. So this would have been positive bending moment, and down here would have been negative if you come below 0. You can come below 0, you know. There are cases when you do come below 0. All right. I'm allowing that to sink in because I need to take it to another level. But I'm allowing that to sink in because we're gonna take it to another level shortly. Do I have a simple one to take it to that level? I'm looking if I have a very simple one. No, I don't. But this slide is quite comprehensive. I'm looking for a simple one. I'm gonna open a simple slide to see if I can find one. So hang on, continue looking on that. I am going to stop sharing for a little bit. See if I find a simple one. Discard. Right. Continue looking at that. Let me just see if I find a simple slide. I want to. Can I find something simple? Well, I see one here. I don't know if I want to show you that one. Because I want to start off with, but the one that I have on my slide there might be a little bit steep. So I'm looking for another one. Hang on a little bit. Let me see if I find a little one. I'm gonna have to use the one on my slide. Others, yeah, I'm gonna use the one on the slide. Now there is what I'm about to show you is we're gonna move it up a little notch. I'm still trying to find a simple slide, which probably will help you understand the next one. All right, we're gonna go to what we call uniform distributed load. But you guys know uniform distributed load. You know, do make correct? Everybody know about uniform distributed load? Like we don't know it, but know this
A
thing, man.
long time that's it.
Oh, when people
Long, long, long,
long
long
time.
time.
Sounds
Ah, man,
familiar.
a long time, man. We
Oh,
all remember that.
all right. All right, so I have one here. Let's look at it and I'll use it to explain before getting back to the major slide. So I'm gonna stop share. I'm gonna look at a simple one here that we have here. All right, let's go. Now, you remember that this is what you call a uniform distributed load. What is that telling you? It's telling you that over the span of the 2 meter, you have a uniform load over that entire frame. So but you can also convert this UDL to a point load. Anybody remember how you convert a uniform distributed load to a point load? How do you convert it? Question I'm asking. If in this frame here I want to convert this uniform distributed load to a point load, how do you do it? This is a nice thing that I need to drop in my slide. How do you convert this to a point load where just a point load is there? So we turn that from a UDL to a point load because they can be converted. What would be its value here? Is it correct to say 8? This would be 8 kilonewtons. If I was to, so I could redraw my frame now and just say, hey, A, B, and if you want to call down here C, and says, this is a point load, 8 kilonewtons, right? This span was 2, this span was 4. Right, now you had a roller here, that means our reaction is here. 1, and you have 2 here. But in this problem, we can ignore the one in the horizontal. And this is AY, and this is BY.
I'm sorry.
Yeah,
If you could, I'm not sure now, but you distribute loads them.
all I'm saying at the question I asked,
Yeah,
how do you convert a UDL
yeah.
to a point load? And what we do, the span. You look for the span that the UDL act, and you use it to multiply the UDL, and you convert it. That's how I get 8. So this is basically what I've done here. So I'm able to work this problem like a normal problem. So I could say that I can find AY and BY, right?
Right. So you have a 4K and now you have a 8K.
Yes, I change it. Look down here. See it here? So this is 4. This is 2 along here. I can find AY and BY because I know the sum of FY is equals to 0. So AY plus BY
Because
minus 8Y is equal to 0. Not true?
Yes.
And if I choose to take moment, let's say
B
at A,
or a big B.
I'm gonna use A. So moment at A equal to 0. It doesn't matter, you know. So if I'm choosing that now, I could say that the first moment is positive, so it's going to be BY times 4 minus 8 times what now?
2.
It's going to be 6. No, sorry. It's going to be 5. Because this is halfway is here, this is 1. And that is 1. It acts in midway. So when you convert a point load, a UDL to a point load, it must act in the center of it. So it acts between here, which is 1.
So let me guess.
You remember that? So it must act 1. That is 1. So therefore, it is minus 5. So So therefore, I can get by from this. So by
So BY would have been -10.
equals to 40. All right.
Oh,
So
+10.
by is equals to 10. So from this expression here, I could say that ay is plus 10 minus 8 equal to 0. So ay is going to be equal to -2. What was that? Kilonewton?
Oh, that's a Newton.
What?
Oh, the Newton. Oh, no, kilonewton.
So this is -2 kilonewton, and this is 10. All right. So you simply have it there. However, when you're doing the graph now, is where the challenges come in. Because for this section is a UDL, and it changes. All right. So you have work it simple. You convert them first, find the unknown, but when you're drawing the graph is where the whole thing changes. So that is what I wanted to share with you first before we actually embark on it. So see it here. So if you look on it, so you can actually start to see it here. So you remember the first one was -2. The first shear force was -2, you know. See, it's gone down.
AY -2,
It's gone
BY
to
10.
right. So you had one that was, it was what? It was 10 across here. So this is -2 from 10. So up here, so it's +8. But because this is a UDL, wherever you have a UDL, people, it's not a simple beam, it's a slope. So the graph is a slope. So for UDL, it's a little bit different. You have to use, it's a slope. See there? It's a slope. So for the shear force for UDL, you get a slope. The bending, the area underneath your shear force give you an idea of what is your bending moment. So this is going to be what now? It was 2 and this is 4. So you know it says 8. So see it here? It's a slope in 8. -8. So the area underneath the bending moment is our guide, give you this. Right? Now between this and that, now you'd have to work it out mathematically because you realize there's a curve. Right? But you, whatever, so you know this is -8. When you work out that value, so you have to find the area for that also. When you find the area for that, then it will give you, when you add it to this value, you know where you end up. What's the area of a triangle? So this would have been, what would the triangle here? The triangle would have been 8 times, what was the distance? 2. So that would end up to give you 8. So, and it would have been what? +8. So +8 and -8. You know, say it is a compound. So a compound gonna give you a curve here below. So you draw a curve. Come right back to 0. Right? So that's a guide how to do the compound one. But we're gonna look at it in more details. All right, so let's go back to our slide. This is just give you an intro. Let's go back to our slide. All right, I wanted to just give you a small intro with that. We're gonna go back to our standard slide. Where is it again? Here. All right. All right, so let's jump back into where we have our slide and it was introducing UDL. Where is it? All right, so we're gonna look at one from the slide now. All right, so let's start off with this one here, so you can get an appreciation. What I want to do, what time is it now, please?
6:48.
6:48.
All right, we're gonna explain this and then we jump into how much time. We have another hour and a half, right? Yeah. So here what we do. I'm gonna break for about 10 minutes, 10 to 15, let's say 15 minutes.
15,
break.
sorry, yeah, 15.
I'm gonna break for 15 minutes, clear your head, and then we're gonna do this. Probably spend another half an hour on it, and then we are going to go play around the lab so we can start getting our labs going. So we're gonna break. What time we're gonna come back to it now? For breaking now.
7:15.
7 what?
7:15.
All right, about About 5 past 7, right? So I'm gonna break, I'm gonna leave this right here. So this is one we're going to look at. So this is simple beam with a UDL distributed load. All right. And what you're seeing is the UDL and the shear force. You're not seeing the bending moment, but let's look on that. All right. So I'm breaking a little bit. Get some water and stuff. You do likewise, please. All right. So I am back. All right, so we have a beam now with a UDL distributed load on it. Now, the span of this is, we have what, 20? Is that correct? That look like that wrong. It's not 20, it's 24. The span is 24, not 20. Can I change that? Let me see. All right, so the span is 24 because it is 12 plus 12. All right, with one concentric load, which is a 6,000 pound, and it has one uniform distributed load. Now, I already told you that how you would find the reactions. If let's say that reaction is not given, how you would find those, you would convert the UDL to a point load by multiplying the span, which is 12 times 1,000. So you would get 12,000 pound. And you would assume that it acts at the center. So it acts at 6 from RA. Right? So all of that, it would act right here in the center. All right. All right. So let's look on the next slide. Let's look at it. Let's break it out now. All right. So we have the UDL, right? And we're summing all the forces in the Y. So it will be R1 minus 1,000 times 12. Because you're converting the UDL to a point load. And that is negative as far as you're concerned. Minus the 6,000 plus the R2. So that would have been your sum of your Y. The moment now would be different. Taking moment at A. So just reminding you how to take moment in these scenarios. All right. All right. So for the first one, if you're taking moment at A, right? So you would multiply 12 times the force to get the point load, to convert to point load. Should be 12,000, but it acts 6 from A, and it is coming down, so it's going into the clockwise direction, which is minus. So it's minus 12 times 6. So that's why you have it right here. 1,000 times 12 times 6. So that's you get your moment. This is your force, that's your moment. The next one now is coming down at this point, which is going to be what? 16 from A. So it's 6,000 times 6, and it's minus. Plus, going up this way is going to be 24 times R2 equal to 0. So that gives you the moment. And from that, you can find R2 and R1 if it's not given, right? All right. Then now we can look at the shear force for the different sections. So let's go and look at the shear force for the different sections. All right. So when X equals to 1, it's going to be 11,000. Because remember now that this was R1. What was R1 value? Remind myself. R1 value was 11,000. R2 was 7,000. So remember this. All right. Good. Right. So R1 value really is 11,000. Right. So that is going up. Coming down at when X equals to 1, it would have been, because you'd have to consider what we're considering 1 right down to to I think 11 or somewhere there, right? You can even write down to 12. What will be the value? Say 1 right down to, we have some value here, 1, 2, down to 12. So when x equals to, so x equal to 1 times 1,000, which is somewhere right here, it would have been 10,000. So that would have been the shear force. What about the shear force when it is 2? So it would have been 11,000 minus the shear, the UDL, right? And you do that right along the span. When it comes down, let's say you had put in 11,000, which is right here. When you put in 11,000, you would know that it crosses 0 because right at that point it crosses 0, right? In this case, all right. What about? So you notice what happened here. It is really x times the UDL. If you were to come up with a formula, and the formula that you would have so far for the first part, right? Cutting into the UDL, it would have been, can I get a 1 second? So it would have been R1 minus 1,000 times X. So that would have been your shear force for the, that would have been that's your shear force expression for right to the UDL, right? Now, so when it is, so, and this, remember, R1 is 11,000. When it reach, when X equal to 11, you know that V is equal to 0. So it crosses right here, right? Because this is 11. When it is 12, it's minus 1,000. So you know, say, gone down here, so, right? So you still have your expression. This would be a relevant expression, right? Now, this one you can't necessarily say you cut it, right? It's not really work out so easy. You can't do method of section on the UDL straightforward. You have to analyze it. It's more analyzing along the way, right? But you can come up with an expression. So whatever the UDL is R1 times 1,000x. So it's UDL times some value x along the span of the UDL. All right. So that's how you work out UDL. So you got the UDL times x minus whatever was there before for that portion, and you find out that right down to 12, you're able to map the values. So when x equal 1, it is 10,000, right? So it's somewhere right here. So when it is 1, it should map down to some value down here. This is 11, this will be 10, and it coming right down. You know, so it's regressing. When it is 2, it's 9. So it's regressing, coming right down. When it reach 11, it crosses 0. When it reach 12, it's minus 1, which is down here. So it's minus down here. All right. 16. Now, what is happening at 16? So it's 11 minus where are we? So that is 12. When you put in 16, where are we now? 16. Okay, 16 is when this 6,000 is right here. So all you do, you would be putting in, you'd add in the 6,000 load to it, right? Which is right here when it is 16, and you'll get what? Minus 7,000. See it right here between here. So you get 7,000. All right. If you notice, this is really a minus 16 value there. Right? It's telling you that when it's have a value right here and a value here. All right. 24. It is right here, down here. What will be the value? That's 7,000 is right there. So it will be 11 minus 12 times 1,000 plus the 6,000. So all of that is the same value right here. So right here, 6,000 is right here. So the 16 start from here, so going right down to 24. Right? So it's 8 between that span is 8. Right? So that's what that is telling you. So from it start from here, which is 7,000 coming right down to here. And remember, it was 1,000 at 16 minus 1,000, right? And the positive 16, it is when I say positive, meaning that you had a positive 6,000 here, right? At this point. So this will be minus this end up to give you a minus 7,000. Minus 7,000 plus 1,000 give you this value here. So this is minus 1,000 here. We had another um 6,000 to it, which is minus, guys, keep coming down there. So another 6,000 to the 1,000 give you the 7,000. So this is really a minus 7,000 up to this point here. So, but it spans right across here. So, and you have a positive 7,000. So it must close back at 0 right here. So everything starts at 0. So the 11,000 start here, right? Now this is a UDL. So the area underneath shear force or UDL is a slope. Remember that. And the slope right across 0. Right? Now, you notice we don't try and use method of section on this. Method of section might be a little bit complicated on this, because if you were, let's say that you were to try and use it, it would be a little bit difficult here, right? Because this is a UDL. So this the method of section is not too straight cut for the UDL. Right? You would have to use your knowledge of method of section and the knowledge of shear force to do it when it is a UDL. Now, this is where it is become challenging, because you're not necessarily going to get a simple one in exam. You're necessarily going to get a UDL. But all you need to know, one, when you're working out the forces, you convert the UDL to a point load. So in other words, when you convert a point load, at the center of it is where you'd consider that you have a 12,000 acting right here, pound acting there. From that, you are able to find all the unknown. Now you look for the span of it, and you come up with an expression for the span of it, knowing all of the forces that you have before. So you know that you had all of the other forces. So like we have the 6,000 here. If you know the 6,000 added to the prior expression, and based on that, you are able to come up with this minus 7,000, because it's minus 7,000 running between that. We'll have to look for more example where, I think I have one more, where you can understand how to manipulate shear force when it's a UDL. So the UDL is not too straightforward when for these beam. You have to just work them out, right? So you multiply the distance time this to convert it to a point load. And from there on, you can simplify the unknown forces. That is the first thing, right? You have to remember that. So in this case, we found that one and we found that one. Now we know the UDL value. All right, so it's UDL times the distance. Now the span across here, so you say you start at 0, you go up to 12. So you're able to work out right across what is the value of the UDL right across. So you know the graph. So you can actually check the graph at that point. Right? So you know when it is 1, it's 10,000. Right? When it is 0, you know so it is 0. It's right down here. It not start yet. All right. But you know this straight line here is the reaction line. Always a reaction line. This now is going to be the UDL. This is the UDL in this case. Right? This is the UDL. Sorry, 1 second. I'm on back in the class. I'll finish up about 8:30. Right. Yeah. Right. So the So right along the span here is it's a graph, right? And you're graphing it. If you notice, it's like you go 1,000, 2,000, 3,000. So you're coming down, but you're regressing. So it's all subtracting from 11,000, you know. So you take off 1,000 from it. Then you take off 2,000, take off 3,000, 4,000, 5,000, 6,000. So 6,000 from 11. So you know where you are right here, so. Right? 6,000 from 11,000, you know, so you have 5,000. Right? You have 5,000 somewhere in the middle here. Right? And you're going down. Right? So you can see it. So this is divided. I think this is divided into 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So you know, so this is divided. So you can actually read this one. So every digit here represents 1,000. So this is 2,000, 3,000, 4,000, 5,000. And that is
Not
really
seeing
how
the
they are.
pointer.
Pardon me?
Not seeing the pointer.
Oh, you're not seeing the pointer. Oh, I'm saying here, for every digit here is 1,000, 2,000, 3,000, 4,000. So all of those are going to be subtracting from 11,000. And it comes down and it reduces it. And that's how you get your graph. Right? So it's 11,000 from 11,000, you know, so you come to 0 right here. 12,000 from 11,000, you know, is minus 1,000. So you drop you below 0. So right here, so that is minus 1,000 there. Right? And it span between here and 4, and it runs across here. Because now you're not UDL again, it come back to a regular thing. So you see, it map out a rectangle, but this is really, a trapezium is really between this point and that point. Now the area under this, you know, say here the bending moment. You have an idea where your bending moment look now, okay? You have to take the area of the triangle. The under this will be area of what? A trapezium, so you know what your bending moment look like at that. And the area underneath this would have been bending moment again. This is a rectangle. So this would have been what this now? This would have been 7 times 6. So that would have been 7,000 times 6,000 is what, 56,000 or something to that effect. Pounds per foot. Right? So that would have been representation of your bending moment. And that would have minus value though. Right? So that's a minus value. So 56,000, but it's a minus. What about this piece here, so? Who can tell me the area between 11, this point here between here is really what? Between here and here, this will end up to be about 5. From here down to this point is 5. What's the area of that trapezium? Who can tell me? Somebody work out that quickly for me. And tell me the area of that trapezium. Who can tell me what that area is equal to? What's that value? I'm waiting, guys. What's that value? That's a trapezium. What's the area of a trapezium?
Your base times height.
Yeah, so what you will get for your bending moment value there, so? For that little part. What would you get for the what about the triangle section? What's the area for that? What's the area for that?
Yes.
What? What's the area for
Yeah.
that? Huh?
Hold on a second. Sir. Sir, area of the triangle would be.
Pardon me? Guys, I
Okay.
really don't read the chat. I don't have time to read the chat. Please talk to me. I know you like the typing and the texting. Don't type your name in the chat. Talk to me directly when you're in class. All right. You type in the chat. I noticed that I saw 32 chats. That's not gonna help me because I'm not gonna necessarily look up there. I'm gonna look up there for registration. All right, go ahead. I saw the comments though, but anything you tell me, just tell me. Let's be brave enough. We're having a conversation. Let's talk to. Are you wrong? All right. And you get correction. Yeah, as you were saying. Yeah, Dixon, back to you.
Anybody else get different value?
What you say again?
You know I say it, but I'm gonna say it anyway. 38,500,000. That wrong.
Yeah, that's wrong. So the first part is really 60,500 for your bending moment. The last part is 56,000. I was asking somebody to tell me the section in between it for the trapezium, but nobody there able to tell me that value there. So it would have actually give us some ideas. Anyhow, we'll look at it chart. We're coming over to it now. So you find, so the first part is 60,500. So it's half the 11,000 times 11. And that gives you 60,500. All right. If you were to find just the rectangle section alone, or if you want to find them separately, you can do it.
Sir,
Yes?
is it a case where you're not on the slide? Because to be honest, I'm not going to see no trapezium.
You know,
Something like that, sir.
Come
honestly,
on.
Sir, honestly.
All right. Fine. Honestly, that is good. You see trapezium here, sir? Want to see the trapezium? Come on, guys. See it here. Anyway, all right. Let's split it up then. Rectangle and a rectangle and a triangle. All right. So let's work out the distance.
Sure, until it go to 1,000.
So this is 1,000. The height is 1,000. All right. This now is going to be what? 4, 4, and this is 1. Not true. You get the gist? So the area of that one would have been half 1,000 times 1. Not true. So that is what? 500. What about this guy here? This one here would have been what? 4,000. Right. Not true.
Yeah, length and width.
Yeah, so that is 4,500. You know, see the trapezium. Trapezium is what? Half the height times the sum of the perpendicular side. Now, so I go. So you have sum this side, which is 5, and sum that side, which is 4. So it will be half times 1,000 times 5 plus 4. Right? Like that? So it's 9 times that. 9,000, half of 9,000, 4,005. You don't see it. That is it. So this trapezium, see them on. We don't see the trapezium, Brandon. Look them on, see there. That's the longer side. This is the shorter side. So them parallel. The height is 1,000. So they are minus. So it's actually minus. So these are minus. So it's minus 5, minus 4,000. So it's minus. This is it. This is it. You get me? You see it now?
Sir, draw the trapezium on the diagram.
Pardon me?
Draw the trapezium on the diagram.
On which diagram? See that, sir? You see it? So that's the longer side, 5. So the shorter side, which is what? 4. So that's a 5, this is a 4, and the height is 1,000. The height is this little piece here now. Remember? You see it? So this height here is 1,000. That is 5. This is 4. You have to be able to spot them little thing there now. So the area for that is minus 4,005. And the area for this is going to be what now? 7,000 times, so this is that, and the height of it is 7,000 minus 7,000. So that's give you 56,000 minus 56,000. So this is minus 56,000. This is 60,500 because remember, it is half. The base is what? 11 times the height is 11,000. So this gives you 60,500 and this is positive. This one is minus 4,000 and this is plus minus how much we tell you? 56,000. How much that work out to? That end up to be minus 59,000. That's all? All right. It's as simple as that. Let's just scroll over. Now if we can mark up on the slide. So look again. Same thing. All right. So now, so for the bending moment, when x is equals to 11, right? When x equals 11 here, right here. So for all of that, we tell says here at the curve, right? So you find it. So it is. So see it here now. So it's minus 11 times 11. So you then work out bending moment. Then the distance times the distance times the force. So this will be minus what now? Some big value there. Then now what they do now with the this is the UDL part. So you have to take the 1,000 times it, you convert from UDL and half of the distance here, which is what 5.5, right? So that's a bending moment because that will be the distance, right? And you end up to be 60. But I'll tell you, easiest way is here underneath this. That's it. All right. So this gives you 60,500. That's an easy way to do it. Here underneath that, the shear force is equal to the bending moment. So it starts from 0 and it moves up to this point here. I think it shifts. I think that is that point. So that right here, so it would be 60,500 positive. Then now, this piece here, so what did I work out it? Minus 500. So it will drop to 60,000 here. Then you're gonna take off another. When you reach 60,000, this is from ear to ear is minus 4,000. So you take off a minus 4,000 from that. And how much you leave with that? So that will give you 56,000, not true? So right here, so it come to 56,000. Positive 56,000. All right. Now over here, no, so it moved from 60, it moved from 60,000 to right here. Is here says it's a 60,000, it's a 56,000, sorry. So 56,000 start here. Because this is where this square start. From between here, this is 4,000 and that was 5,000. So it dropped from 60,000 from here to 60,000 here. Then it dropped from here to here. After you take off another 4,000 off it from here. So 4,000 from here to here. And when you reach here, so which is 56,000 now, it goes to 0. Right? Because remember, we tell it always, anyway it start to finish. Remember now we have a negative. This is a negative 56,000 when you work it out. So negative 56,000 and positive 56,000, you must come back to 0. So this is the bending moment diagram. If I was to, wow, what is going on here? I touch one thing and everything unravel. Where am I? Right. So when you reach right here, I was drawing a little graph here. Oh, my hand is on something that is disrupting the process. So this is positive value. So the positive value over here would have been 60,500. That is your maximum bending moment. Right? If I ask for your maximum bending moment, that would be your maximum bending moment. And where did it occur? Right here. Right here, so it occur. right? Then the other value would have been right here. So when it dropped another 500, minus 500, so it dropped to 60,000 right here. So, and then from 60,000, it got to 56,000 because it's from 60,000, I take out 5,000 from it, you must get 56,000. So it dropped from here. So, right? Because remember, these values are minus, you have to work with them. These are positive 50, positive 60, 6,500, but everything down here so is negative. So when you work them as negative, you have to keep subtracting them coming down, and you keep the negative from them, and they will carry right back down to zero. You start at zero, you end at zero. Same thing for the shear force. So this is maximum BM. If you ask a maximum BM, this will be your maximum BM. And this is maximum shear force would have been that value up here. All right, next one. All right, suppose you get something like that now, guys. All right, everybody remember this now? All right, what do we really have here? We have a UDL running right across the span of the beam, and the span of the beam is 32 feet. 3 concentric load and 1 uniform distributed load. All right, it says construct the shear force diagram, designate maximum shear, and locate where the shear passes through zero. It's a mouthful. So you look, and one of the things that we can do, you always can convert your UDL to a point load. So if you multiply the entire 32 times the 500, and you're at the center of that beam, you're going to drop it. So if it's 32, you know that is what? 16? 16, wherever 16 drop, you know says where you convert it to. So you're at the center of it, wherever the 16 drop, you know that that is the center of your beam, whatever it is. So it's 500 times 32, whatever value that is, but this is the center of, you convert it to a point load. So it's a convert UDL to a point load, it must be here. So you work with 1, 2, 3, 4 load, and you work out R1 and R2. All right, so let's look and see how it's done. All right, so as I told you before, now we see the values here. You know that one is 0. You start with this one and you sum, that's negative. You have one also here. So you'd have draw your free body diagram and you put your R1 there, remember? And you would have had your, you know that you have a UDL in the center. You convert this to the point load, so you'd have it whatever its value. 500 times 32 would have been its value. So that's point load. So you'd forget about UDL once you change it to point load, you know. So that, this, that. So you'd put, so it would be minus 20, which is the first one, that's here. Then you have the positive R1, which is here. All right. Then you have minus 12, which is coming down, right? Then you have R2 again, positive, see down here. And the next, and this one coming down is 5,000 times 32, is minus, see it here? So all of that would give you the sum of Y expression, right? Let's move on. And then now, after that, you would have worked out, you'd have been able, all right, now you take moment at A now, because you need to lose. I would take moment at probably A. If you call here A, take moment here, all right? Is that my A? Yeah, whatever. You take moment at A and B. Wherever it was our A and B. I think our A would be yeah. So let's go with it. Oh, this is the A. Pardon me. I'm sorry no. Hold on, guys. I probably mix you up. Hold on, let me step back. This is not where R1 is. I'm sorry, I wasn't looking. This is where the supports are. Let me look back. Go back. Go back. Yeah, so this is where your R1 and your R2 is. So we call here A, and we'll call here B. I'm sorry. It's kind of a little fine sometimes. Can you see the slide properly, guys? I come into presentation view. Is it too small?
No, sir, it's all right. It's all
All
right.
right, good. Yeah. All right. I lose it there for a minute. Let me just clean up. I've lost my concentration to see where I'm at, what is on the diagram here. Let's get back to it. So I have to write. So I'm sorry. I know its pointer is a little bit small. So this is our A and our B, as we said before. So let's move back to the other one. Come on. All right. So the A is not here. The A is right here. See it here? A, B. I've identified them. All right. So I just got this thing here and I modified so that we can use it to explain. So we got that one. All right. So this is one when the UDL running right across it, you know. You can imagine. So we're gonna take moment at A. So you know that R1 going to drop out, but R2 will be involved. Going to find R2 now. So let's take moment at A. You take moment at A, is going to be 2000 times 8. See it here, and it is anti-clockwise, which is positive. All right. The next one would have been the 12. So the 12 will act in what now? 4 from A. 14, sorry. 14 from A. See it here? And it is going in the clockwise, which is minus. So see it here? 12,000 times 14. And then the next one would be what now? What is that distance? 24? Looks like 24. 14 plus 6, 24. So 24 coming for the 4,000, and it is also minus. But at the center of this, we have a UDL. You remember? We convert the UDL to the point load. So this is going to be what? 500 times the 32, which is that value. But what is the distance from it? The distance here, this, what was the center? It was 16. From here to this point is 16. That's all? That was 16. So how does 16 work? If here so is 8, then this is 8 also too. Not true. All right. So now from this point now it means it's 8. 8 from this point here. So we go. So it's see it here now. So it's 500 times 32. Right? Right? And what distance they have here? They say it act 16. So I work it out to 8. Basically, am I correct here? Let me just check that distance, please. They have 2 divided into that. What are we having here? Minus 8. My distance is incorrect. I'm checking that distance. So it's 32 minus 2. Where am I? Just checking that distance here. So it's 32. Why are we getting 32 here? Let me just double check this. Where? We have 32 here as it's supposed to be 35. Hold on. Yes, this is 32. Correct. So, okay. All right. This is correct. Because half of this is going to be what? 16. 16 from 8. So it's 8. Right. So I worked out my way. So it's 8. So that distance is 8. So you could have actually just said this times 8. So 8 from 16 is still 8. So it's 8. All of that is 8. All right. And then plus this R2 here. What is that R2 from here? So it would have worked out to be about 20. 14 plus 6. So see it R2 times 20, but it is going in which direction? Anti-clockwise, which is positive. So you see it there? Taking more in from A, so you get R2 from that. And you, all right. And also to get, why are we here with this? Well, you could do it also taking R1. So it's 2 ways it show you to do it. So you could also take moment at B. That was the objective of putting this here. So let's take it from B and look at it. If you take it from B, let me clear up this. Don't want anything before to confuse us. If you take it from B, right. Let's go with it again. So if you take it from B, where's B? B is right here. All right, and we still have your UDL in the center. This distance we know is 8. What is this distance from here to here? That is another challenge. But if you know the one before, you know that coming from down here was what? 16. So if this is 10, 10 from 16, so you know, so this distance, hold on, not so fast. This was 6. So from here to here, we assume that is 6. So coming from here, so it's about 12. You see it? From where, hold on. From where this UDL to this is, this point load now, because you convert it to point load. So it's 12. All right, let's just look at it now. So where's the 4,000? 4,000 coming from this end, and it's, what's the distance? It's 4 here, and it is minus because it is clockwise. So it's 4,000 times 4 plus, which other load you have? The 12, and the 12 is acting 6 from it, and it is positive, so it's 12 times 6. All right, the next one now would be the 2,000. All right, the 2,000 from here would be, what is that distance now? That look like 28. 6, 14, that look like 28. Where am I? So it's 2,000 times 28. Right? Got the 2,000 coming from all this way. So it's 28 and it is positive, right? The next one would be the UDL, which I already tell you that it is what? It work out to be 12. So it's 5,000 times 32 divided by 16 minus 4. So that is 12, right? So that's 12, right? Minus now, this guy here now from here. What is that distance? It look like 20. So it's 20 times this one. So you can find R1. Instead of find R2, you can find R1. So it gives you 2 options how to do it, right? Not just one. All right. So you find it, R2 is 18,800. And then you find R1, whichever method, that means you'll have used that one first. No, so? Yes, you'll have, it would be equation 3. This is coming from equation 3, not 4. And then you substitute it in this equation here. Well, you work out that and you get R1. So you know that value from this equation, and you put it in this one now. This one here will give you this. That means whatever you get here, you take it and put it in equation 2. So this is coming from equation 2, I am assuming, right? So you put R2 in that, and you get R1, right? And if you do the same thing down here, it's the same thing, you put it in equation 2, right? So it's your choice. All right, let us move on. I know it's quite a bit. All right. So this is a UDL, and listen to me, guys. Ask question if you're not understanding. Don't keep silent. All right, now they're taking moment. It says take moment 1. I suspect that they're taking moment at here. See that this is R1, right? If you're taking moment at R1, so it would have been what now? Minus 2,000 times 8. We actually did it a while ago. Plus 12,000 times 14, which is what now? So it's 2,000. Oh, I'm going to point out something to you guys. You see in this one here, oh, this moments expression is written. I borrowed it from somewhere. They use a different convention. They are using the clockwise as positive. Didn't realize. So the clockwise is positive in this one here. Let me check if the others are like that. I wrote these. I think I modified them because they were kind of, yeah, I think I had gone in and let me check it. So this one was 2,000 times 8. It was positive, right? But you see this one around here, I didn't get to convert it. It has a different convention. They are taking clockwise as positive in writing out this. And I do the same thing with this one here. I didn't modify this. So I must warn you. That's a different convention used to write this particular one. All right. So, and what this is, let me see what was written around here. You have 3 and 4 around here. So I've actually have an expression here for R1, R2. Right. So the expression here is different. Right? Different expression. Determine reaction. All right. It means therefore maybe this slide can be dumped. I think this slide here is a little bit redundant. It could actually, I think, really and truly, I've rewritten them here. See it here? So I've rewritten it in my convention, but this slide should have been really dumb. I think this slide can dump. Because look, 3 and 4 here, equation 3 and 4 is the same thing. Yeah. So it's repeated here. That means this slide should have been dumped. I'm just recognizing it. So I modified it. I went through and modified it, but this was a redundancy because I realized that it was not saying the convention that I was using, but yet still it wasn't deleted. All right. So I recognize that. Let's move on from that slide. Recognize what is going on there. All right. So this is now you can see how your shear force look. Remember the shear force now. Let's analyze the shear force. Now, as I told you before, because of a UDL on it, we can't just use the method of section on this. It's not a straight cut thing. All right. So when x equals to 8, there are two values. They are saying that there's a minus and a plus value. So they're analyzing. If you notice, all of them, they put a minus plus. That's their methodology of analyzing it. Let us see if we can understand what is going on here. So when x equals to 8, what is happening here? You have a reaction here. And this reaction is
There, you're
15.
fine. Make it bigger, please.
All right. So when x equals to 8, right? So we go 2000, 0 minus 2000, right? So we're going down to this point here. 0 minus 2000, because you start 0, then you go minus 2000. Because this is coming down negative. You're looking at all the force you have down to where x equals 8 is. All right. So you got 0 minus 2000. But up to this point here, so you have a UDL running across here. And this UDL, what is the value of your, so in other words, you can convert this UDL to a point load up to this point. So it's 5,000 times 8. So see it there, but it is minus also. So two things, minus 2,000, minus 5,000 times 8, give you minus 6,000. So up to this point is minus 6,000. You're getting effect right at 8 here. So see there, minus 6,000. All right, moving beyond here, so going that way now. So they have positive 8 on 8 for the distance. So they're saying going this direction now. Let's analyze it. So they're moving from here, so now going down. So it's 1500, which you know is going up. So this is a positive force. These are negative force coming down, so that's why you have the minus sign. The positive force now going up. So you have a positive force here. You also have a positive one here. So this one is a positive force here, so now. So you have the 1500, all right, and they put minus 2000. So they're checking them. So the minus 2000, see a minus 2000 there, right? Minus the 5,800. So they put it back into this one now. So this was when the forces are coming down negative. These are when the forces are positive. This is how they analyze it. All right. So this is one way of doing it. So you go 1500, which is this positive reaction here, minus this 2000, minus this. You see the UDL, the convert UDL, which is 5,000 times 8. See it here, and this is also minus. So these two minus here. Remember, these are give us what? Minus 6,000. So it's minus 6,000 from this. So the minus 6,000 from this give you 9,200. So you get two values here now. So you got a value that it was minus 6,000. Then you get a value that is 9,200. Because listen to me, this is a shear force that representing the negative shear coming down as a result of the conversion of the UDL to a point load plus this, right? That would have been what? 8 5s 40. So that's what? 4,000. Am I correct there? Follow me now, man. 8 5s is what? 40. So
Sure,
you
yeah,
get 4,000. So minus 4,000 and minus 2,000, you get minus 6,000. So all of those negative shear coming down between this point here, right? When you have UDL on it, it is not straightforward like a regular beam. So you get this minus 6,000. Now, what about the force going up here now? This force is going to be taken away from the to have the negative shear coming down. So you have a big positive shear going up, but a negative shear coming down. So there's a difference between it. So it's the 6,000 from the 5,000. That is actually what happens here. Repeat it here. So those two are covered up to this point now. Let's move on from this point and when we're going. So look, see it here now. So the minus 2,000 come down, 6,000 come here, and it's underneath. See, look, they are negative, you know. Negative there, come down to here. They're all negative. The difference between the 6,000 and the 5,000 is 4,000, which is right here. So the UDL, so the UDL and the slope, show you that is a UDL. Between here and here is 15,200. This is 6,000, but this positive shear is 9,000. See it here, sir? 9,000. Now, we're moving over to which load now? This one here, sir, and this shear force. The shear we have here is going to be what? 500 times 14. That's the UDL coming down. That is one of them.
Sir.
What?
Sir, just a quick question.
Mm-hmm.
What's the difference with positive X and negative X?
All right, I was explaining to you that this is representing the negative shear. This is representing the positive shear for the same distance. So this is telling you that the negative shear that is occurring, negative 2,000 and the negative 4,000, which is the UDL right here. So see it here, minus 2,000, minus 4,000 give you what? Minus 6,000. See it here, minus 2,000, so this is 0, minus 4,000 added to the 2,000, give minus 6,000. But at the same time, you have a positive reaction going up here, so a positive shear, which is 15,200. The difference between 6,000 and 15,200 is 9,200. So you have to draw a line going up there, so you're going up back. You're going up in a positive shear. All right, now let's cross over. Now, down to this point here, what's the distance? 8 plus 14 is 22. See it here? So the 22, we're looking at the negative shears first. How much negative shear we have? We have the negative shear here and we have that. Let's look at it. So it's 1,500. So remember, you know, up to this point, you have the 2,000 here, right? Now, the negative shear up to this point over here, so is what? 22? All right. So let's look at it. Now, if you look at it this way, one way of analyzing it is that you say that you have a positive shear here. So the positive shear here, you reach at this point. The next negative shears you have will be these forces taken away from it. So this is going up, but these are coming down. 12,000 plus 500 times 14. Let's look at it. So here you have it, 2,000. So you have to repeat everything before that you had before, please. Remember, so you have the minus 2,000 plus, let's look at it, minus 2,000 times 500 times 22 says all of these are coming against this positive shear. All of the negative shear coming down, so you're repeating yourself again. So look, 2,000 plus this distance here is what? 22, because 8 plus 14, this is 22. So all along the span of the beam here says 22 times 500. Where is it? So 500 times 22 is minus the 22, minus this because what? This is going up to this point here. So that's 22, and this is a negative, working out the negative shear that is happening. Now this value here gives us positive 2,200 from this reaction here, coming from the negative this side here. All right, so it ends up and give you 2,200 up to 22. So this is where your 22 drop you, right? At 22 now, all right. Notice you have a 1,200 there now. All right, force coming down. Let's look at the positive side of it now. So you have the 1,500 minus the 2,000 minus the 1,200 minus this. So you repeat yourself again, but you include this guy here. This is one way to do it. There are other ways. So you work out the 1,200 minus this part, which was 500 times 22. What's that value? 500. Somebody would even jump in and tell me the value. 11,000. So the 11,000 minus the 12,000 minus this give you minus 9,800. So see it here now? It comes right down and drop down here. So this is minus. But what you need to remember is the 2,200 plus this give you 12,000. So when it comes here, it must come here. All right. And another way, and this is a shear force, so it's tricky, but you know say it's slope, because for the UDL here it is slope. What you must remember, you see this point load here, it must work out to be 15,200. So it means 6,000 are the difference here. It must work out, right? That is what you really need to, and you must remember that it's slope. From once between here is slope. So everything here is going to be a slope. See there? Slope down. But here, so you have to deal with the load you have here, the point load, say go up 9,000. Then you're gonna slope again, slope coming down, right, to 2,200, right? But you see how we work out the 2,200? We call that the negative part of the shear. So you look at all of the negative force coming down from the 1,500, right? Same 1,500, the last 1,500 you deal with, which was a positive shear, positive force. Is all of them, in fact, you know, is taken away from the 1,500. All right. So the next one, down to, when you reach down to here, from the same 1,500, they're all going to be taken away from it. So this is one way of working it out. 2,000 from the 12,000 plus all of these are negative force coming down. So all of that, this is negative. The UDL coming here says negative plus this from this positive force here. So see, that's how you get your minus 9,000 here. This again, now look, all right, we're gonna move up to 28 distant. 28 is where? It's 8 plus the 28 is right here. All right. So, but this is the only positive force coming up, so everything is going to be subtracting from it. So you're going to repeat again. So where we are now, so it's 1,500 minus the 2,000, repeating again, plus all of these distant coming up to here. So 2,000 minus this one coming down, right? Times 500. It was 500 times 22. It is 500 times 28 now. Can you come right up to here? This is all of the level of the UDL, right? Equal to minus 12,800. Right, so see it right here. So now it's sunk between, so the difference between the 8,800, so it's split, this is 6,000, so it's come down here, right? So you know where we are. So come down here, then this is 12,800. When you reach at this point, you know that there's a 18,800 going up. So you have to add some value to this to bring it up to 18,800, which is what? 6,000. So 6,000 come across a positive zone if you were to add that to it, right?
So
All the way. So you're
sir,
moving this way now. Look, going that way, go this way, you're coming down, you come down, and you come down, right? But the fact,
sir,
go ahead.
yeah, when you're working out the negative 28, right?
Mm-hmm.
Why the 15,200 still included the positive?
All right. All right. This, as I said, there's many ways to do it. This is one approach. The reason. All right. Let's look at the frame. The frame. Look at how many positive forces you have. You have two. All of the other forces are negative. Can you see that in this particular instant?
Yeah.
Right. So all of those are negative. So, and if you notice what they do, in this case, we started out on the 8. So every distant, every span, we consider negative forces and positive forces. And what they do, so the negative part of it, look, minus 18, we start up to here, but we consider just a force across here. So we didn't put in the 1,500 yet. We just consider this one alone here. So you consider this span here and that for that part. All right. Beyond this point now, this force comes into play, where you have to consider all of the span of it from this guy here. So then now, here now we put minus 2000 minus this distance for this, for to see what is happening right at this point. And from there on out, we use the 1500 because it is affecting everything along the frame. This same 15,000 effect along, and remember now the span running right across. So look, so we are at, when we reach 22, what we finish, that is minus forces coming down, and this is a positive shear, because it includes positive shear. Minus now, you're going down right down where to 22. So 22, and you start all over. So you keep using this because this is only positive force in this instant. Now you don't do all problems like this. This is one approach, I'm just telling you. This is one approach where you have a UDL spread right across it. I don't think you'll never get something as challenging as this in exam, but we have to show you different examples. So 22, down to 22, you're gonna have negative shear and positive shear. So this 1500 here, subtracting everything that is coming down. If you notice it, everything that is coming down, subtracting from it for the negative. For the positive shear is where now we had another, the positive 22 is when you have that other point load away from it to see what is gonna happen there. So you had another point load here to hit, and you get a minus value for this section, which is right here, right? So you have a plus, minus, and a plus section, which you get shear forces. You're looking to see what is going to happen at the plus side and the minus side each time there's a load added to it, and that is really what it does. So they work around this, coming up to a certain point. Actually, right up to 32. Right, so this is the approach, because this is a UDL which is quite unique. As I say, you won't get anything as difficult as this, but this is just giving you an angle to it. So up to where the negative, so right here we would have been at 28. Where's 28 again? Right here, right? So you would have been at right here. So you're working out that value. So it's 1500 minus 2000 minus 12 minus that. You keep working them out so you get a minus value right here. You're right here. So you move from here, you're down here. All right, because this was the last value, which was minus. And the next value from this now, let's take and see what happens. So the positive 28 now, you know that you have a positive big number there, 1800. So you're gonna add it to it, right? In this case, so these two had right here, right? And then you have minus force here. You're gonna have all of this, then minus 12 also coming up to this point. But also, what about the span? The span is going to be 500 times 28. So it give you what? Positive 6,000 right across here. And the last one now, the same 1500, you're gonna add back the force again. So these two are positive here because you have a positive. These are bigger shear. The bigger shear minus the smaller shear. See what happened now at that point. So these two, if you notice when you reach here, so these two shear start adding right along here. So for the 32, which is on the other side, you're gonna be minus the same 2000 minus the 12, right? Right, because you want to see what happens, you're gonna get at that point. You don't put the 4,000 in it, you know, you're working down to it. So you get the higher values here, minus that value coming down, and you span everything coming down to this point here, right, to 32. So see this one is down to 32, and you put the 12 in it, and you get 4,000 positive. So it tells you now, you move from here, get 6,000. Between 6,000 down to here, you get your 4,000, right? And then at this point, this is positive 4,000. You have a negative 4,000 going down, so you must close back at 0. So this is positive 4,000, guys. This is negative 4,000, so you're closing back at 0. Now, guys, as I tell you, you won't necessarily get anything this challenging, right? But it's there as an example, right? We normally just give you one UDL and move on. So the maximum vertical shear, is what we have here. So it is 12,800. It's really minus still, but considering ignoring the value, that's really the maximum shear. Ignoring the value. So disregarding plus or negative notation. Shear passes through 0 at 3 points. It passes through here at this, where this reaction is, passes where the 1200 is, and it passes where the 18. So you see it passes through 3 times. R2 under the 12,000 load. R1 and R2. So these right here, so the 1200 is affecting right across here. All right, so let's look at some rule of thumb. It says shear is dependent on the load and reaction. When a reaction occurs, the shear jumps up by the amount of the reaction. When a load occurs, the shear jumps down by the amount of the load. Point loads create straight line and shear diagram. I'll explain that further. Uniform distributed load creates slope line and shear diagram. All right. Did this change a while ago? All right. Moment is dependent upon the shear diagram, right? So the ear height, your shear force give you your bending moment, right? So the ear on the shear force we are equal to the change in the moment, right? So that's something that you need to remember. Straight line on shear diagram creates slope on the moment diagram. I'll show you shortly. Sloping line on shear diagram creates curve and moments diagram. Positive shear equal increase in slope. Negative shear equal decrease in slope. Those notes are there for a purpose. Go through them and understand it. Typical loading, and I'm going to show you some more. In beam design, how much time we have? We have time for our lab? Or I should stop here. Oh, let me stop here and go on the lab. I'll come back and finish up on this. Come, let's go to the lab. As I was explaining before, and I probably need to send another link so we can play around with the lab and start it. All right, this is the lab. All right, hold on. Before I show you this on the lab, let me. I was hinting before. Where is the lab now? I am looking for my lab. Not finding the lab. Hold on. Is it not here? It's still here. Hold on. Let me. Hold on. Okay. So like it. All right. So the lab is this. All right, and it's on your. I think I put it up since it says investigating adding force with a force table. So the goal is describe the effect of 3 balance force acting on a ring or disc using vector addition. To practice adding force vector graphically and mathematically in a simple geometry. All right, so you're gonna read this. One of the most important point is that I have modifier here so to form with the force table simulation that you have. So you're gonna position one pulley to apply a force at an angle of 248. Call the force exerted by the string F1. The force the second force we call it F2, and you can set it at. So these values are you're gonna set them at these and see what happens. See if you can balance it at 98, right? So you call the force F2, and then the third force will be F3. Now the third force is when you lined up with 0. This doesn't necessarily apply. What you have here in the notes here is a guide. It is how you do it physically in a lab. This notes is showing you. So look at it. So for example, the one that we have, we're gonna get that wherever you're down here, we're gonna start from 0 and you're gonna go right around to 360. So it's not gonna start like this one, right? But this is a force table. So our thing is gonna start at 0 and then it goes around and you try and balance them. So let's just look at it to give you a good picture of it. That's the best way to do it. All right, so this is what it looks like. This is your force table. you get a disc projector, protractor, you get a steel ring, which is this ring around here, and you get the masses. All right, so let's jump to it. Now, couple things. Angle 1 is for F1. So this is F1, right? Why do I know it's F1? Because this is what, see it move F1 there. Angle 2, it moves F2 here. So see F2 here, right? And F2 have a maximum range that it can go, right? And it has a minimum. So you have to toggle it. See it go 30, and I think it can go up to about, I think 200 or somewhere there. It goes right up. Now, the objective of it is to balance all three forces so that F3, which is this guy here, right? F3 is this guy. By the way, they don't have a F3. This is F1, F2. Now, you can add weight to all three of them.
F3 0.
Yeah, F3 is really 0. Yeah, it's 0, really and truly. So it's supposed to line up with this 0 right here. That's what F3 is supposed to line up with 0. These 2 0, it must line up. So you start here and go right around to 360. Now, yeah, so it's F3 is really 0. F1, you can put weight on it from 10 up to 90. Your choice. F2, which is going to be this guy here. So you can put weight on this guy here, which is F2. You can choose any one of these values here. Right? And then now F3, you can also put weight on F3. Same thing goes. You put any weight on it. And then you go to F1 and F2 and try to balance it. Now, we have weight on them. Let me see what we have on F1. We have 90. Let me drop it down a little bit. 70. This one, put it at 50. And this one, 80. All right. So let's see if we can balance it now. All right. So let me see if I can shift it around where we can see it. All right. All right. So you see it? On the objective, we want to line up this. It look like it pretty much line up here. It's not really perfect. So let's see if we can line it up. Look. So it's really to line it up. It look line up. Is it line up, guys? You agree? It look line up. I think. All right. Let me see. So it's supposed to line up. We can look carefully if it line up, you know.
So, sir.
Yes.
So what this basically do to make it center line up?
Yeah. The objective is this. All right. Let me show you, for example. Let me move it out of line and show you.
Sure, what site is this?
What?
What site is this you're using to
Is F, I can't remember. See it there now? See it move out the line there now, so you know so the weight them no balance. So it's an equilibrium, you know, you're trying to get these forces to be in equilibrium. All right, so that's what the force table does. So my thing is to line up back it to 0. This guy here must always be at line up here at 0 point. So you get it and you line it up, and then you use vector. You can draw your diagram. So we have to get it to line up back. I will see, is that looking good? And you can turn it around and look at it. So it looks line up to me, and you can take out the value. So for this is now what? This is F2. So F2 is 100. Draw the quadrants and notice. Let me show you something. This is, I would consider running a quadrant right across. 4 quadrant. You see over here where 90 is. If it is 90, then it is 10 above the quadrant that you normally call your X and Y positive. You see your X and Y positive, it is 10 above it. I can't write on this thing here. Unfortunately, I can't write on this. Can I write anything over here? So in other words, your quadrants, if for this, I would say that my first force is up here. And this is 10. That is that one. What is, that is F, oh, that is F2. Yeah, F2 is where? So F2 is above here. Remember 90 runs right here. Right, so you're 10 degree, you're 10, I'm consider 10 degree right here for that first one, and that is F2. F1 now, where did I say F1 now? So let me drop this off again, see if I can get one. So right, so you see this one now, I'm considering that you have, if that is 90, I'm considering that there's 270 across here. This is 0. So I'm coming right around to 360 here. Right back around to 360 is ending up back around here. So you're coming right back around to 360. Now, if this is 270 and I'm getting what's that value? 236. So the difference between 270 and 236, how much is that, guys? What's that value? What's give me the value. What's that value? Come on, class.
234.
34.
234.
So 34, right? So that force is going up there. Now this one is coming down here to 0. Remember? So the objective is that you're gonna use, this is equilibrium of forces. You're going to draw you are now going to draw, you can use graph paper. And the objective is that these two forces must sum up to be this one here, right? So it's equilibrium of forces. So you can do your vector. Now, if this is coming this way, it should be that way. If this is coming this way, it should be that way, right? So the both of them, you should be able to do a tail to tip. So this is F2. No, sorry, this is F1, F2. So let's say you do a tail to tip and you draw F1. Not F1, F2. Can draw anyone first. All right, so you draw that one and this is a 10. You do a thing here, and now you're going to draw this one here, right? So you're going to draw that one at what, 30, 30. So this is 34 up there. So you know automatically there's a 10 underneath there for that angle. Now this one is going to represent your, when you join these two together, it represent your resultant. And that is it, right? That is what you're supposed to do. So what I want to ask you to do is to do it about 5 to 6 times. And you're gonna, each time you draw your sketch, you should be able, one, to do it by, you use a protractor, you should be able to do it by measurement, use a scale. Now, the weight of the forces, we have them. In this case here, what is the weight of the force? The weight of each force, we know them. Let's look at it. So the older is 10 plus 70, and this is for F1. So let's write them down. So F1 is total force is going to be 70. Remember, this is gram, you're going to do your conversion, plus 10. So that is 80. F2 is going to be hold on. Come on, where's my writer? Going to be 50 plus 10, 60. And F2, F0, you're going to find that. So we call it 0, but you're going to find that. The angle that it is 0, but you're going to find the actual F. So F3 is not given. You're going to find F3. That is a question. So each one of them find F3. So you do it about 5 times, right? And each person gonna write up on it, and you're gonna read up on force table. So you're gonna find F3. We already tell you what to do here. So you're going to do it and show that the principle that it is true from your analysis, right? So the weight, actually, what is F3 weight? We actually have F3 weight, you know, but you can do it and check it. We have it. Sorry, we have it. It is really what now? What is this one? 80? Yeah, we do have it, but you're going to prove it. That by calculation and your graph that it works. So it's 80 plus 10. So this is 90. Right? And you convert that to kgs and work out the Newton. So remember, these are all grams, you know. So you're going to do it. You're going to prove that when these two add together, you get that value. You're going to do it by graph and prove it. Not just by the force table, but you're going to prove it. Right? And you're going to prove that they're also in equilibrium. Right? And there's a lot of literature on force tables. So I give you a little bit there in that thing, but there are others. So don't believe that my thing is going to be the sole information. I'm looking to see if I can find some other little ones to show you about your, let me see if I find one more. Oh, I don't find any. Hold on. Statics lab. I'm trying to find some more for you. Hold on. See if I find some more. I want to show you some more labs here. If I can find. All right, this is what I folder that I'm looking for. Let me stop share and show you. All right, so as I was saying, force labs are basic. All right, so let me see if this one have anything to show you. So it shows here, it says adding of forces, and it shows you about the basic adding of forces, eh? And it's the same basic principles. See them here, paragraph of forces. So you have F1, F2, that line. So you can draw for me a parallelogram to show that this one plus that one give you this. So you can actually draw it by scale. Same thing that I showed you before. So you can use the head and tail method, or you can use the parallelogram rule. Any which one of them, I'm all right. So it's equilibrium force acting at a point. When several forces act at a point, their sum can be obtained according to the rules of vector algebra. Graphically, the sum of two forces, F is equal to F1 plus F2. So F3 is really the sum of F1 plus F2 for vectors. Can be found by using the parallelogram rule illustrated there, or equivalently by the head and tail method, which give you a triangle one. So which I show you. The sum of the vectors can also be derived analytical by adding their components. So you can also add the components. So you have a force table, and it says the condition for a transitional equilibrium. So it's the same thing, all right? So you can use it. You can use either this one to display it. I want you to sketch it. You have the angles. Draw it up using your protractor and your compass. Basic, man. You can do it about 3 times. You don't have to do it more than 3 times. Do three of them, and you can do it. You can actually, the one that I have right here now, you're free to use it. This one here, I think everything went while I was playing around with it, but let me see if it's still there. Right. The fact that I jump out, everything went, eh? But all our sketch. But see there, it is 0, and we know the values, right? We know them, you know, we have them. You want the values? You can use these values for starter. 236, and this is for what now?
Sir.
This is F1. Yes?
Did you say the name of the application, sir?
Pardon me?
I don't think you told us the name of the app that you're using here.
Question. You guys want to do it by yourself, or you want us to do it in the class? I don't have a problem doing it in the class, you know. Because when you're on your own, I don't know what you're going to be doing. Let us do it in the class. Let us spare another 5 minutes and do another 2. All right. So we have this one. Take off that one. This is F1, angle for F1, and the force F1, right? And as I tell you before, do it. I suggest you use this to kind of give you a balance. So you would say that this is 0, 90, 180, 270, and you come right down here, so back to 0. So this one, F1 would have been this one. No, that is not F1. Is that, yeah, F1, the angle is what, 2 something? Hold on. F1, which one was F1? This one was F1, I'm sorry. My F1 is right over here, I'm sorry. So the angle here was what, 34? F2 was what again? Let me go to F2. F2 was 100, so this is 10. Someone said something. So this is F2, and this was F1. I'm mixing them up. This is F3. So you're going to prove that when you sum these two, it actually gives you this. So even if you have the value for it, I wouldn't know the value for them. Let us work out, let's write down the value for them again. So F1, F2, and F3. So we know the values, you know. It tell you the value, but you can actually prove it by drawing up the sketch and find the resultant, which is going to be that guy. So let me tell you the values now for the weight. So the weight for F1 would be 70. You can 70 plus 10. F2 would be what? No. It is 50 plus 10. And F3 was what? No. So this is what you're proving that it will give you. You must draw a sketch geometrically and mathematically to prove that this is what you're supposed to get. So this is supposed to be 90, but you know this is grams, so you have to convert that to kgs and to Newton, right? So you must, so this is what you're really proving, you know. So you're proving that F3 is equal to F1 plus F2. That is what he essentially proving. We put the vector up there so you don't get confused. So you know that this will be having Fi x and Fi y. Right? So you know that you have I components with these and likewise these. These two add together and you can use Pythagoras or whatever. But from here, remember what I said to you, you know, you're using this to prove. So we had sketches a while ago. If I sketch it back, tail to tip. So we had saying that if this is 10, and you come back and you construct a cardinal here, the next one is going what? That way, tail to tip, 34. You know that is 10, so you know so that it end up to be 44 in that case. And then now these two join together, it's supposed to work out when you finish. And you must use a scale. Use a proper scale, people, right? Whatever that is. And you can do it mathematically, but you must also show it on paper that when you do that and have these scale together and you measure this with your measurement instrument, it gives you back that value. So yes, you must prove. That's what you want to do. If that, everybody understand that? All right, we're gonna select another few, right? We're gonna select another two and change up the values now. Are you ready? Please write them down now. I'm gonna change up the values. All right, so for F1, we're gonna change up some values. Put that as 50. F2, I'm gonna change it as 80. And F3, I'm gonna call it 40. Let's go to them now and see if we can balance them. So I need to erase what I have around here. Where is the clean screen now? Don't even see it. Clear all. Clear all, John. Yeah. All right, so let's just balance it now, no? All right, let's see if we can. All right, so we want to balance it back here. Let us quickly try and balance it. All right, let's move the F2 up first. See if we can. No, let's go. All right, let me get in there. Is that balance? No, no, look perfect. Come back down. Is that looking balanced? It's out. This is not making it at all. All right, means we need to go back and adjust. All right. Let's check that. That looks close to it. Is that looking center? All right. Yeah. So you can take off these values now. So you have another one. So this one is, let's see if we can map what we have here in this case. So this was 0, 90, 180, and 270. We know 360 come back around here. All right, so you come right around. All right, so what do we have here? We have for F1, F2, sorry. F2, this is 140 from 90. From 140. How much we getting, guys? 50. So we have 50 for that one. All right, for F2, 50. Oh, that is looking fine. So come on. So this is F what? F2. All right, next one. Where are we here now? We are below or above. Can't see this one properly. You have to help me with this one now. Let's get the value for it. F1. F1 was how much is that? 270? 276. Oh, cool. All right, so we have the value here now. So if this is 270, so this is 6. All right, cool. So now you should be able to draw these two forces and get the resultant, which is going to be F3. So you can use parallelogram of forces. I don't mind parallelogram of forces. I love it actually. So if you're using parallelogram of forces, you're gonna draw, what are you going to do? You're going to go with F2, which you know that is what? Okay. And then what you're going to do, you're going to draw this guy here, 6. And then you're going to draw another one up here, 6 to that. And then when you stop that one, you draw another one parallel to this one at what? 50. Pass. And then now where's your resultant? Your resultant would have been which one now? Where's the resultant? Is it here or is it there?
Yes, sir.
Yeah.
That 6 wanna be below the 270.
Hold on. Am I reading it correctly? Where we say we're going? We're coming down 270. Oh, hold on. Yes, you're right. Thank you. Yes, it's really below. Thanks. All right. Somebody's watching. Good. It's below. Beautiful. So that would be wrong. So it's below. So wherever you have that, it's below. So it's becoming below. So yes. It's below. So it's actually wrong. So it's right. And then you find the resultant. You would have done the parallelogram. Oh, that orientation there is bad now. That would have to clean up. Let's go with that. This one is totally right. Yeah, you're right. You're right so much. Are you still seeing it, please? I see something about pause here. Are you still seeing it? Hello?
Yes, sir. Yes, sir.
I see something about your screen sharing is pause. All right, I touch it back. All right. All right. So let's construct it back. Hold on, let me move that. That's not relevant. All right. So, all right. For the first one was 50. All right, so you draw your 50. And the next one was what now? 6 below. All right. And then now you would have to draw another one parallel to this. So each one you do, so here so you do construct and draw another one at 50 to this. So you wait for your 90-degree run, 50, you construct the next one, which is parallel to this guy. And then likewise you do it up here, where this is 6 below, you construct that one to it. All right, so that to that. And then now you draw your resultant, which would be that line. Am I correct? I think that would be the resultant. Please check it. Which direction? Where are our direction, by the way? We would, or is something wrong here? Something is wrong. This is erroneous. I'm sorry, this is wrong. Come again, the tail to tip wasn't correct. I think I'm a little bit tired. So the first one would have been 250, correct? Up here now you construct the 6. The 6 will become below, wherever you have the 6 coming below. All right, you have that one. Right. Then now you would choose if you're doing parallelogram of forces, then you know you do another one parallel to this one here. And then likewise that. Right? So that would be parallel to that. And this is parallel to this. Right? And you know your resultant. All right. So you and you look at arrows. So you're going so you can check yourself. So that will be coming down. All right. So that is it. And you can draw it. So that is 2. Can we do one more before you guys go? Hello? Can we do one more? So we get some measurements there.
Yes, sir.
So
All
we're
right.
gonna give you mass.
We're gonna give them mass. All right, let me give you the mass.
We're gonna get the mass then for this
All
one.
right, let me give them mass them now. Write them off now. So the mass now would be all right, so the mass now would be F, so it's F1, F2, F3. So F1, remember this one is a check and balance, you know, because you actually know that, you know, and that is what you take. So F1 now is going to be 50 plus 10. Because remember you have to put in the 10. F2 would have been every time I have to change between them for it to work. All right, next one is this guy here. So it is got now 80 plus 10. So that is 60. This is 90. And this is one that you check and balance in. You actually have the value, but you must prove it that it is correct. Next one. There's a vector lab you have. This is 40. 40 plus 10. This is what you're working to prove. So that gives you 50. And remember, these are grams. You need to work them out and turn them into newtons. So you convert grams to kgs, right? And you multiply by 9.8, and you get them into and please don't use no 10, you know. 9.81 for G. So if anybody come to me with anything different, you know, come with me a 10, you know, you'll get a 10 mark. Done. All right. So remember now. All right. So that is those weight. You want to do one more before you go? Because this is your lab, you know. You can do one more. All right. Let's do one more. We're gonna change up the weight before we go around. I'm putting that as 30. All right. I'm putting this one here at 50. Putting this one here at 80. Let's see what is how we can work out now. And I want to clear screen. Clear all join. All right. So this one now, let me see. Is it still balanced? Let me see if it's still balanced. No, it's not balanced. It's a little bit out. It's skew. It's not balanced. Let us balance it. See what this one work out to be. Let me carry it up so you can see that it's not balanced. All right, so we need to get that to balance. No, let's go to this one. This one look like it's not too hard to balance. All right, it looks like it's 0 now. That wasn't bad. Oh, it's not perfect. Let's go back to this one. See, we want to get the bottom one to be balanced. The bottom one don't balance. It's not in the 0 perfectly. Notice it. Look. Can look at it from different angles. It's not. We're not seeing it. I was trying to get this one balanced a little bit more. Let me see. No, worse. It's not perfect, you know. Let's go again. Worse. All right. Let's go again. Coming close to it. All right. Let's see this one now. This is more to hit. Let me see that. All right. How's that look? That look better or worse? Better or worse? Class, how's that look? That one all right? It looks more to 0. Everybody gone to sleep? How that one look? Look a little bit
That
better, eh?
can work.
Just trying to see if it's 0. All right, so let's write them off now. So F1 is, right, so you can see your value of your forces. F1 is, this is 270, 90, this is 0, 180. So this one here is, the difference between 270 and that is what now? What's that value? 34? Am I right? I'm tired, you know. If nobody talking to me, what is that?
Yes, sir.
34.
30.
34. All right, and that is going up. All right. The next one now. 150. So 150, that 90 from 150. How much that? 60?
60.
All right. So you have 60 here. All right, let's look at the weight them now. All right. So the weights them, which could actually write them down from we set them before. Next time around, we could have write them down. So it would be, so F1 is 30 plus 10, 40 grams. And F2 is equals to 50 plus 10, which is 60. And then the next one will be F3. I remember F3 is, you have the value, but you have to prove it. 90. So this is the one that you're really proving. You're proving that F1 plus F2 is equal to F3. So you must show that when you finish graphing it and by calculation that you get this value here. That value, whatever that value is supposed to be, 0.090 times 9.81. Right? So you, whatever that value is, you must prove this value by calculation and by graph. Get a scale and draw it. So at least 3 of them. And you write up your conclusion. Now, the sheet that I have posted, let me stop share. Let me just go back and give you a view who want to see it again. All right, so see it there, you can sketch it down. See, all right, this is what your table look like. So you must present you can go on the internet and read up on force table. You must present your graph. Let me remind you of
Sir, what
something.
table? We are up on that big old circle thingy.
It's a force table. It's a force table. All right. So in your lab sheet, where's the lab sheet that I showed you before? I think it was this one. All right. So it's not necessarily gonna look like that. Your one is a little bit different. But down here, so I put some value down here. So you have the mass 1, mass 2, angle, and the angles there, and the balance. So you know F3 really, we get the value, we know the value, still put them in. This is always at 0. Right? But these are the 2 values that we change. So you see a table here, you can modify it or use it. You must have your aim, apparatus, diagram, procedure, and method. Is some people say the same. You can have a theory too. You can put a theory in it if you so desire. So you put theory in it, right? The result table, the calculation, the precaution, and you must have your drawing. Sorry, make sure you have your drawing. The drawing will include in your scale drawing. I should say scale drawing. All right. So you should have your scale drawing. Please modify that because I don't have that on the website. So you have your scale drawing, we're going to draw your thing to scale, right? I don't expect anything less. Have your scale drawing, don't mess. Make sure you draw up and we can see either your parallelogram of forces where you use your parallelogram or you draw your parallelogram. So you have your vectors, right? So so you must show it, right? You must show it. Your resultant force, which is going to be equal. So your resultant force is going to be equal to F3. Remember, F1 plus F2 equals to F3, which F3 is really your resultant force, right? It's the same thing as parallelogram of forces, right? I have a similar lab to this, and it's basically the same way. I normally call it gravestone bridge, but it's the same principle. And I probably mark it. It's very same way. Just the difference is the apparatus, right? I probably need to show you that table, and I'll mark it on the same principle. I don't know if I can put my hand on it right now. Let me look, see if I have it. In fact, the time is finished. I will tell you next week, but start working on the lab, please. Start practice calculate the scales. You have 3 of them, you know, everybody can use that. So your first lab is basically on the way. Some of you want the link to practice the thing, I can try and give that to you. Right, so if you want the link, I can share that. All right, I try to remember to share the link. All right, some of you really want to.
All right, sir.
Yeah, man. So yeah, the link.
Prepare this recording here, sir.
What?
The class recording.
You recording? Yeah.
From last night on tonight.
Yeah, these are it here. These are the I probably just I could send you guys an email or send it to let me try and see if I can send it now to you. The best thing is to do it. Everybody put their name in the chat. Please make sure everybody put their name in. In fact, let me take down the register right now and I'll do the others afterwards. Select everybody. So I'm copying note now, you know. So make sure you have your name down. It's time to record attendees. And notice that there are a lot of persons not attending the class and not hearing from them, and them say they're doing the course. Since I'm teaching, Horace has not spoken to me once. And at the end of the day, people are gonna say they do the course. You can't do the course and you're not communicating. I don't know where you get that from. It can't work. It just can't work, guys. This is registration. All right. I trust that class was meaningful. You have a lot of work to do. Please go and read up the slide. And read the textbook too. Work the problems. So by Friday, you should be getting a multiple choice, either 5 to 10 questions. Remember that now. Please prepare yourself. If you want, I can put it on the weekend. You prefer it on the weekend?
Weekend.
All right, I'll try. All right. Especially I'll consider persons who work. I'll try and put it on the weekend for you. All right. So, all right. Fair enough. So every week going forward, you're probably gonna get a test. We have to step up our game. All right. So that you will keep practice and get sharp in the areas. Especially when we do the topics, you know, just take it for granted and just forget about it. And you're not reading, you're not practicing. Those two don't work together. You have to keep yourself agile, working constantly. Remind yourself what you need to do and do it, you know? Practice. So this is my way of assessing you through the unit test. All right, guys. That's it for me for this week. All right, so you have your lab. You have a lab sheet. You can make whatever modification to it. You have your bridge. We have at least one more lab to do. We try and do that next week. Bending moment. We'll see if that one can work. I have another simulation. All right, so I am going to try and send you probably using OneNote. I'll use OneNote and see if I can send it to you just now. Let me see if that can work out right now. Right. Remind me, what's the email again, guys? Your email, I know the group have different email. Oh, I could actually use my email and send it to you guys. What if I post it in Moodle? I wonder if you could access it that way. Which one is better for you?
Moodle would be all right if it could do that way.
Yeah, that's a consideration. Because it's 2 emails I'll have to send it to. That is another one. That's a little bit problematic. Let me go into Moodle and just paste it in one of our file there. Sometimes I can't remember the emails. All right. All right. The Zoom link, if you guys notice, every week I have to be changing my Zoom link. There's a problem with, I'm having a problem with PCC Zoom link. Unfortunately. So every class I have to be doing a different, right? Get a different one. They just don't work. So that's part of my problem. I did one today, and by the afternoon it's not working. All right. So, all right, I'm gonna put it below the lab and put it in a, so, hold on. I'm gonna do it as a label, see if you'll be able to pick it up as a label. I hope you'll be able to pick it up as a label. Oh Lord, this is the wrong one. Let me see if I can pick it up again. All right, so I have it here as a label. I hope you can. Let me see how it is displayed. All right, so they are there as a label. So they are below statics force lab. I have different labs there, not all of them. Let me see if I make sure that is the right one that you get. All right, so there's one for the beam. That's the last one. Last one is the beam one. Hold on. All right, those should work. I think it's the first one. So just look at the first one for me. My Moodle screen just went. Look at the first one for me. First one should be good to go. All right. Anyway, guys, next week. All right.
All right.
If you're having difficulty, you can always send